In this video, we're going to be looking about inverse functions. But what I'd like you to do first is take a minute and pause the video and try these 4 out of the 2 now. You'll be able to complete E as well after, but take a minute, pause the video, and just try that out. So what you might notice is that we've got composition of functions in A and B. So composition of functions meaning you're doing a function more than once, right? F of 15 is closer, so we plug that in first. So I go to f of x and plug in a 15 there. So 2 times 15 plus 9, 39. And when I plug that answer into g of x, then we get 39 minus 9 divided by 2, which gets me back to 15. Same thing in b, right? We see g after f. That's what the little circle means. So f gets done first. So 2, plug in a negative 3 plus 9, we end up with 3. And then when I plug that into g of x, I end up with negative 3 as my answer. Now, C and D mean we're plugging in the actual function. So g of x already is what it is. It's x minus 9 divided by 2, as we see. So if I plug that into f, where x was, I get 2 times that whole g of x plus 9. And what's going to happen is those 2's are going to cancel out. And I have x minus 9 plus 9, and I have a final answer of x. Same thing, if I have f of x, 2x plus 9, if I plug that in for the x of g of x, I get back to x. So what I'm looking at is that these functions undo each other. So whenever I have 2 functions that undo each other, they're known as inverses. Now, when I go to look at this algebraically, I have f of x equals 3x minus 2, and g of x equals x plus 2 divided by 3. They're inverses of each other. We got to prove that, though. So basically, the way that I can go about proving it is by showing that when I plug one function into the other, they can get back to x. So in this case, it doesn't matter which function you do. Let's say I did g of f of x. Well, if I plug f of x in for the x of g of x, that means I'm plugging in 3x minus 2 as x plus 2 divided by 3. And just like we saw in the do now, I'll be looking at 3x over 3, and it gets me x. So that's how I know that these are inverses of each other, right? Now, in that same regard, there's a little stipulation here with this one because I'm dealing with a square root function. So if I look at this, let's say I plugged in x squared and for g of x, right? Or either way, like if I want to switch it up, let's say I do f of g of x this time. So if I plug in square root of x here, I'm going to get back to x. So it's going to work out. But there is a little stipulation. Let's go see why. So if I take a quick minute, bear with me as I rewrite my screen here. I'm going to add a tab for Desmos. And when I look at that, x squared and the square root of x, you can kind of see a relationship here. Now, imagine this part was not here though, right? I can't fully get this down here because we know we run into an issue with negatives. I mean, I can't have negative output, so that's why we know that x has to be greater than or equal to 0. Bear with me, I don't remember exactly how I get that part to show that situation, especially when it's there. But imagine this part's not here. Then I see something like this. Now, so let's get rid of these 2. Let's go look at the one prior that we just proved. So if I go back to the one prior, it was 3x minus 2 and x plus 3 over 3. Now you might see something that we saw in the previous one too. basically, everything here is a reflection over the line y equals x. Okay, if I bring back the x squared and the square root of x, you can see that as well. But remember, there was the stipulation here that anything here did not count. It had to be x was greater than or equal to 0. So what's happening, if you remember your geometry, let's take a quick peek here. Let's add my table in here. So if I look at this point, let's say on my green one here, I've got 2, 4. But look here, 4 and 2 is also on this graph. 0, -2, -2, 0. So if I go to try to find some nice points, even like this -8 down here, so -2, -8, if I go to -8 over here, what's happening is, if you remember your geometry, the line y equals x, when we reflect over it, switches your x and y. That's what makes an inverse its function, by switching x and y. And let's go see that a little further here. Now, just some things that you should know always is that an inverse is represented by the notation of this little -1 in the exponent spot. Big things for you to know is that it's not an exponent. You're not raising something to the -1. Instead, it's just notation. So when I look at this line here, 2/3 x minus 2, like we saw here, we're definitely reflecting over the line y equals x. So here we go. We've got this point. It is at 6, 2. So now my next point is going to be at 2, 6. I've got this point 3, 0. So 0, 3. I've got this point 0, -2. So -2, 0. I see this point -3, -4. So -4 and -3. And I've got this point -6, -6. Well, you switch those points, it's still the same thing. But you'll keep in mind that this line here, that's y equals x. That's what it's reflected over. That's what means to be an inverse, is to be reflected over this line. Now, just some maintenance things here is, if you see something like this, notice we normally know it as f of x. But now, if you have the inverse, that 2 is a y value. So you can think of it as the y value of 2 off the original here. Or you can think of what the inverse line is going to get me. So when you look for 2, we end up with 6 here. So remember, it's saying the y value of the original 2, or you can look at your new line here, that reflected line. So if I do the inverse line and look at the blue, if I go to f of 2, I go up, I get 6. That's the same as if I go on the original line and do the y value of 2, the only value there is still 6. Same idea. If I go to -4, if I go from the original point here, original line of -4, that means I'm going down to y of -4, and that's going to get me that value of -4.
3. Now, in the same regards, right, if I go to the inverse line that I've already created, if I go to -4 there, I'm still getting -3. So it's your choice of which line you want to use in that case. But the y-intercept of the inverse is clearly at +3. You would get that by finding the x-intercept of the original. So basically, the big idea is that you switch x and y. So don't get caught up. You see this -1 piece here, this idea of an inverse. People love to switch the negative sign for some reason. That is not it. It's just switching x and y. So something as simple as that, knowing that switching x and y is the case. So now we want to figure out what the inverse is. Again, your first step always is to switch x and y. Now you might be saying, hey, this is in function notation. I don't have a y value. Remember, this is equivalent as writing it with the y, but your big rule is that you switch x and y. Now, in this case, we've switched x and y. Now, it's like your literal equations back from Algebra 1. You're just trying to get y back by itself. Now, the thing to notice at the end is that I'm going to write it in inverse notation again. My inverse of that original f of x is this, which makes sense, right? You're subtracting the 7 over and you're divided by 2. Okay. When I look at something like 6 here, you can do the same thing. Now you can have something that's in the inverse and you want the f of x. It's the same thing, right? You still set this up y equals x minus 3 to the third plus 1. Now your idea here first, of course, is to subtract 1. Oh, excuse me. Of course, the first thing I should do is to switch x and y just to help get that idea organized. And then I can subtract the 1. So I got x minus 1 equal to y minus 3 to the third. Same as before, right? Now you're just taking the cubed root from both sides because you have the third power up there. That will cancel. That will leave me with the cubed root of x minus 1 equal to y plus 3. Minus 3. So my last step is just to add that 3 back over. And my final answer will be that f of x originally was equal to the cubed root of x minus 1 plus 3 outside of that cubed root.
Now, the big part of these questions here, remember, is they love to ask you questions. These two here are the kinds that they would ask you for a short answer on the Regents exam. So, in this case, when you're doing this, we know we're looking at y equals 5x over 3x plus 1. So now we have multiple x's. I'm going to change x and y, which means I'm going to rewrite every piece to be y in this case. And whenever you're dealing with fractions like this, I'm going to stick that x over 1 because then we can cross multiply. I'm going to be looking at 3xy plus x equal to 5y. Now, the part about this that gets a little tricky is like you want to make sure that y is on one side. So I'm going to subtract. So I'm going to have x equals 5y minus 3xy. I'm going to use my factoring skills here where I pull out a y. Because now I have y isolated. I'm right there. So the part that I want to do next is divide 5 minus 3x to both sides. Because then I've got x divided by 5 minus 3x equal to and that y, but I can rewrite it as the inverse there. That's how I rewrite this here. I switch x and y and get y by itself. Now, there's multiple answers you could get for something like this because I could have technically
I could have subtracted the 5y and subtracted the x. So I could get some things like I could get a negative x over a negative 5 plus 3x. That is a valid answer too. Just show your work. As we know, we have multiple things that can be equivalent, but there are two answers for this question. Same as this one down here for 8. Same kind of thing again. In this case, if I want to skip, let's go ahead and skip around. I know that the f of x equal to y, but I'm going to set it equal x is equal to 5 minus 4y over 3y plus 2. So every x value is now y. That f of x is x. Same thing as before. Stick that over 1. We're going to cross multiply. So I'm looking at 3xy plus 2x equal to 5 minus 4y. Now I want y's together. So I'm going to add the 4y. And in the same step, I'm going to subtract the 2x. So I have 3xy plus 4y equal to a 5 minus 2x. You could have negative 2x plus 5. It does not matter. But the whole point is that I got to use GCF in here so that I can pull out that y. Our goal is to isolate a y value in this case. And once you've isolated y, I can divide that other piece out. So my inverse is going to look like 5 minus 2x divided by 3x plus 4. All right, you're going to have more questions like this to help you get some practicing on that, but we will practice more together when we're back together in class. All right, thanks for watching.